Hello, I'm Joseph Kasser, and welcome to this podcast where the AI team does a deep dive into some application of systems thinking.
Welcome to the deep dive. If you're joining us, it means you're someone who likes to get under the hood of complex topics and really understand the mechanics of how our world actually works. Today, we're taking a hard look at the very DNA of how we build complex systems. Our mission for this deep dive is to unpack a fascinating, it's a February 2026 draft manuscript by Joseph Kasser titled From Systems Science to Engineering Practice.
Yeah, and it's a really provocative piece of work, to say the least. But before we get into the weeds, we need to establish a crucial baseline for you listening right now.
Right.
The framework and the principles we are about to discuss today are explicitly candidate or proposed principles.
Yeah, that's key.
Right. This is not a finalized prescriptive standard that the engineering community has just carved in stone. Kasser is putting this forward as a starting point. It's a conceptual scaffold designed to invite challenge, refinement, and collaboration from the field.
That is a vital disclaimer to keep in mind. So framing this as a set of proposed solutions implies there is a massive underlying problem that needs solving, right?
Oh, absolutely.
The manuscript introduces what it calls the undesirable situation, which is essentially a 70-year identity crisis in the field of systems engineering.
Okay, let's unpack this because, frankly, that sounds a bit absurd on its face.
It does.
You would think a discipline responsible for putting humans on the moon, developing global telecommunications, and building the internet would know exactly what its own foundation is.
I mean, you would think so, but it's a fascinating historical paradox. The crisis fundamentally exists because systems engineering, or SE, has historically conflated the activity of engineering with engineering management.
Okay, how so?
Well, to understand why, you have to look back to 1969. The U.S. defense acquisition world published a standard called MIL-STD 499, and its purpose was just to describe what a systems engineer actually did day to day in a massive defense program.
But in doing so, they basically codified a job description, right?
Exactly. They formalized what the manuscript categorizes as SETR, or Systems Engineering the Role.
Right. That standard was heavy on administration. You know, requirements tracking, configuration control, organizing technical reviews, managing budgets. That is project management.
Yeah.
What it completely failed to define was SETA systems engineering the activity. SETA should be a rigorous scientific discipline focused on how discrete parts interact to form a functional whole.
And because the discipline effectively took a government procurement job description and just copy-pasted it into an international standard, it never built a foundational bedrock of actual science.
No, it didn't.
Which totally explains the warring camps the paper talks about. You had a process-focused camp, a problem-focused camp, a life cycle-focused camp.
All arguing.
Yeah, they've been arguing for decades about what systems engineering actually is, but they were just looking at different facets of an institutional job title. They weren't looking at the physics or the logic of systems themselves.
Precisely. They were describing the bureaucracy of the role, not the disciplinary core of the science. Kasser's draft manuscript aims to resolve this identity crisis by building on his earlier work with Hitchens.
Okay.
The ultimate goal here is to shift the industry's focus away from how the job is administered and anchor it toward verifiable, tangible outputs that are grounded in actual system science. And they propose doing this through a completely new structural four-layer framework.
Let's break down this four-layer framework. It's structured like a pyramid, designed to give engineering practice the same kind of indisputable foundation that mathematics has.
Exactly.
At the very bottom, forming the base, is layer A, systems axioms. These are universal, accepted starting assumptions. They are fundamental truths about all systems, whether you're talking about a biological ecosystem, a social network, or an engineered spacecraft.
Right. Concepts like systems evolve over time or uncertainty is an inherent property. You don't prove these through experiments. You accept them because denying them just breaks fundamental logic.
Yeah, and sitting directly on top of those axioms is layer B, which contains the system science principles. These are the scientific generalizations derived logically from layer A.
They describe how systems behave universally across different domains. But, and this is the crucial pivot in the manuscript, science is not engineering.
Right.
Science is descriptive. It describes what is. Engineering is prescriptive. It's about what we do to intervene in the world.
Which brings us to layer C, the systems engineering principles. These are action-oriented propositions. They take the descriptive science from layer B and adapt it specifically for human-made, intentionally conceived systems.
Yes.
And this layer C is the primary focus of the manuscript, and it's going to be the engine of our deep dive today.
Just to cap off the architecture for you, layer D sits at the very top. Those are the systems engineering processes, the day-to-day tools, the specific software you use, the operationalized workflow.
The daily grind.
Right. But layer C is where the profound shift happens. What's fascinating here is that this hierarchy strictly separates the underlying science from the management bureaucracy. It dictates that a true engineering principle isn't just a best practice or a vague corporate goal.
Right. The manuscript is adamant that every single principle in layer C must be verifiable.
Uncompromisingly so. A principle has to see what the engineer does, why the underlying science of layer B makes that action strictly necessary, and crucially, it must produce a measurable output.
A tangible thing.
Exactly. An engineer has to hand over a physical or digital artifact that can be evaluated. It transforms systems engineering from a collection of good ideas into a rigorous, accountable discipline.
Okay, let's get our hands dirty with these candidate principles. We'll start with the first one, SEP1, mission grounding.
The great place to start.
The core concept here is that an engineer must discover the real need in the operational environment before they ever start drafting system requirements. And the verifiable output you have to produce is a formal mission statement that isolates the exact problem without accidentally dictating the solution.
This is deeply grounded in the scientific axiom that a system's purpose does not exist in a vacuum. It emerges entirely from its relationship with its environment. The most expensive, catastrophic mistake you can make in engineering is solving the wrong problem flawlessly.
Yes.
Purpose isn't something you just inherently know. It has to be aggressively discovered.
The ISR data fusion example in the text illustrates this perfectly. If a military contractor gets a requirement that says, improve data fusion, what are they going to do?
Build a database.
Exactly. They're going to build an incredibly massive, expensive database architecture because that's what data fusion implies.
Right.
But if you actually force the engineers into the operational environment to do mission grounding, they might discover the boots on the ground don't care about database architecture. The real operational need is reduce time to target identification from 47 minutes down to 8 minutes, specifically in a degraded communications environment.
And building a system for that specific mission leads to a completely different engineering path.
Totally different.
You might end up building a highly decentralized, latency-optimized processing pipeline right at the edge of the network, rather than a centralized database. They are two totally different systems, costing vastly different amounts of money, because one team jumped straight to a presumed solution, and the other grounded their work in the real-world operational problem.
Which naturally brings up an interesting tension when we look at SEP, interaction architecture.
Yes, SE2.
The directive here is that you have to design the interaction structure, meaning the interfaces, the contracts, the information flows before you're allowed to design the physical parts. The output is a formal architecture specification.
Right.
But I have to push back a little here. How is it practically feasible to design how things interact when you don't even know what components you are working with yet? That sounds incredibly abstract for an engineer who just wants to build something.
It does sound counterintuitive if you're used to bottom-up engineering, but it's essential because of how complex systems actually function. Behavior is an emergent property.
Yeah.
It emerges from the parts and the interactions between those parts. If you just pick the parts first, you are letting the interactions happen by accident.
Can you ground that in a real-world example?
Take autonomous vehicles. Stability on a highway at 70 miles per hour isn't a property you can program into a single camera, or a radar unit, or a steering actuator. A camera isn't stable.
Right.
Stability emerges from the precise microsecond interaction between the perception system taking in data, the planning algorithm deciding what it means, and the physical control mechanisms executing the turn.
So it's the space between the parts.
Exactly. If you design those components in isolation and just wire them together at the end, you are crossing your fingers and hoping stability magically appears during integration testing. By forcing the design of the interaction architecture first, you define the absolute latency limits and data contracts. You make stability a deliberate mathematical output rather than a lucky byproduct.
I see. So the interaction is the architecture. That makes perfect sense. But mapping out how things should talk to each other is still a static exercise. A blueprint doesn't show you what happens when time and delays enter the equation. And that's exactly what SEP3 addresses, solution system modeling. The requirement here is to develop conceptual and dynamic models before you commit to that architecture.
Yes.
You have to produce a concept of operations, or CONAN-PS, and a dynamic behavior model.
Because a static blueprint is blind to time. Delayed feedback loops, not component specifications, dictate how a system actually behaves over a period of weeks, months, or years.
The classic example the manuscript uses for this is the supply chain bullwhip effect. And honestly, anyone who lived through recent global supply chain shortages has felt this firsthand.
Oh, absolutely.
You have a system where every local node, the retail store, the regional distributor, the overseas manufacturer can make totally rational, logical decisions based on the limited inventory data they have in front of them.
Yes, their individual behavior is flawless based on their local reality.
Right. But because there's a significant time delay in the feedback loop between a consumer buying a product and the factory ramping up production, the whole system starts oscillating violently.
It spirals.
Exactly. The retailer overorders, the distributor panics and triples the order, and suddenly you have a massive glut of inventory 3 months too late. It's a dynamic failure. A static map of a supply chain looks perfectly fine. You absolutely have to model the dynamics to see the collapse coming.
And once you model those dynamics, it forces a very uncomfortable conversation about responsibility. That is SEP4, boundary negotiation.
Right.
The engineer's job here is to formally establish what is inside the system's control, what is outside it, and what is merely part of the background environment. And you must negotiate this explicitly with the stakeholders to produce a formal boundary specification. System viability is entirely dependent on its coupling with its environment.
The air traffic management example in the text really hammered this home for me, because boundaries aren't just technical lines drawn on a whiteboard. They are literal contracts of survival.
Exactly. Imagine you are designing a next-generation air traffic management system. If you just casually assume that the aircraft transponders, the devices broadcasting the plane's locations, are perfectly reliable, you are categorizing them as a given.
Right. An assumption.
Yes. You are placing them completely outside your system's boundary and therefore outside your responsibility.
But if someone starts spoofing those transponders with fake signals, or they degrade due to solar interference, your entire million-dollar system goes completely blind and collapses.
Precisely. But if you formally negotiate that boundary during the design phase, and you classify transponder reliability not as a given, but as an environmental factor your system must actively monitor and influence, everything changes.
You design differently.
You will design redundancy, cross-referencing radar, and anomaly detection right into the architecture. Negotiating the boundary forces you to build resilience against the environment, rather than just hoping the environment behaves itself.
Okay, so we have grounded the mission, modeled the interactions and dynamics, and negotiated the survival boundaries. Now we actually have to build the thing. That brings us to SE5, hierarchical coherence.
A crucial step.
This principle states that you must derive each subsystem's objective explicitly and mathematically from the whole system mission. And the proof is a decomposition specification with strict performance budgets.
Because complex systems are inherently hierarchical. You have to break a massive project apart so different teams can build the pieces. But if you don't enforce strict coherence from the top down, you end up with subsystems that are locally excellent, but collectively disastrous when you put them together.
NASA's Apollo missions are the ultimate masterclass in this. They didn't just point to the thousands of contractors and say, build the best parts you can.
No, they couldn't.
They had a total mission mass budget that was ruthlessly allocated from the top down to every single tiny subsystem. If the engineering team building the lunar capsule let their specific design get too heavy, even if the extra weight made the capsule arguably better or safer locally, they were violating their budget.
Yes.
Because that extra mass degrades the launch vehicle margins, which requires more fuel, which cascades until it degrades the reliability of the entire moon mission. They maintained hierarchical coherence through budget traceability.
It was arguably the only way a project of that scale could succeed. But getting a system launched is only day one. Systems have to survive the test of time, which is what SE6 covers, lifecycle design.
Right.
You must design the system to accommodate foreseeable evolutionary changes across its operational life. The required output is a lifecycle architecture. This ties directly back to one of the foundational truths, axiom A7 systems evolve.
If your design assumes the initial operating context is going to stay frozen forever, your system is doomed. The comparison the manuscript draws between the Maginot Line and the F-16 fighter jet is such a stark illustration of this.
It's a profound contrast. The Maginot Line, the massive defensive fortifications built by France before World War II, was technically an engineering triumph. The concrete, the guns, the logistics, they met all their internal specifications perfectly.
But they failed.
Because the foundational environmental assumption that Germany would attack head-on in a war of attrition was entirely rigid and ultimately wrong. The environment changed, they bypassed the line through Belgium, and the system couldn't adapt.
It was a static monument. And then you contrast that with the F-16.
Right. The F-16 evolved from the Block 1 variants in the late 1970s all the way to the Block 70 variants flying today, over 4 decades later.
Right.
Why did it survive? Because the original engineers made a deliberate architectural decision to physically and logically separate the stable elements like the aerodynamic airframe from the highly volatile changeable elements like the avionics, radar, and weapons computers. They didn't just build a jet, they designed a platform for evolution.
We're designing for adaptability from day one. That's brilliant. But let's talk about the models we use to design these adaptable systems, because SEP7 tackles multi-model coherence.
Yep.
The requirement is to manage a set of complementary models and explicitly map out the contradictions between them. To prove you've done it, you output a coherence specification.
This touches on something deeply fundamental about systems science. It's tied to the epistemological limit of the field.
Meaning the philosophical limit of what we can actually know or comprehend about a complex system at any given time.
Exactly. No single model, no matter how sophisticated, can capture every dimension of a complex system. A geometric model shows you space, a thermal model shows you heat, a behavioral model shows you software logic. Every model intentionally omits information to be useful. The risk isn't that you are using multiple models. The catastrophic risk is failing to manage the dark spaces, the gaps between those models.
So the manuscript uses the Therac 25 radiation therapy machine as an example here, and it's a deeply sobering one. It perfectly illustrates the stakes of ignoring those gaps.
It does.
The engineers had a software behavior model that worked. They had a hardware timing model that worked. Neither model was inherently flawed in isolation.
But the reality of the machine existed in the space between them.
Right. There was what software engineers call a race condition, basically a fatal timing glitch, where the hardware and the software were trying to execute contradictory actions at the exact same microsecond.
Yes.
But because that glitch existed entirely in the unmanaged gap between the software model and the hardware model, the residual uncertainty was invisible to the engineers. 6 patients tragically died from massive radiation overdoses because the contradiction between the models wasn't treated as a coherent engineering problem that needed to be mapped.
It is a devastating reminder that ignoring system interactions has real-world, fatal consequences. And that reality leads directly into the final 2 principles, SEP 8 and 9, which explicitly deal with consequences, foresight, and ethics.
Let's get into those.
SOP is unintended consequence analysis. The directive is to identify second-order, feedback-driven effects before the system is deployed. The required output is an unintended consequence register.
Now, here's where it gets really interesting, because it's easy to just say predict the future, but the manuscript makes a really vital distinction between 2 types of unintended consequences. Type 1, which are genuinely unpredictable, and Type 2, which are predictable but unmodeled.
That distinction is the crux of the principle. You cannot engineer away the genuinely unpredictable. The universe is too chaotic. You can only design for resilience. But you absolutely must engineer away the predictable but unmodeled consequences. A failure to do so is a failure of professional rigor.
Let's look at the 2 ecological examples from the text because they frame this perfectly. Type 1, the unpredictable. When ecologists reintroduced wolves to Yellowstone National Park in 1995, they obviously knew it would affect the elk population. What they didn't predict was that changing the elk's grazing habits would allow willow trees along the riverbanks to recover.
Which brought back the beavers.
Exactly, which brought back the beaver population, whose dams literally changed the physical morphology of the rivers. You cannot model that chain of events perfectly ahead of time. It's a Type 1 surprise. But then you look at a Type 2 failure, like the cane toads in Australia.
The 1935 agricultural disaster. They introduced the cane toads specifically to eat the cane beetles that were destroying crops.
Right. The designers deployed the toads. But the toads couldn't reach the beetles, completely ignored them, bred out of control, and their toxic skin poisoned almost all the native predators on the continent.
It was a disaster.
The sheer absurdity is that the broad ecological interactions, what the toads could reach, what their natural predators were, their toxicity, were entirely knowable facts in 1935.
They were.
If someone had bothered to do the systemic analysis, they could have easily predicted the disaster. But because the secondary effects fell outside the narrow intended design boundary of kill the beetles, nobody modeled it.
And we see this exact same type 2 failure repeating constantly in the modern tech sector. Think about social media recommendation algorithms.
Oh, absolutely.
They were meticulously designed with a very specific, narrow boundary, maximize user engagement. But the reinforcing feedback loops of those algorithms ended up amplifying fringe, polarizing, and outrage-inducing content across global populations.
Which was completely predictable.
Exactly. That wasn't an unpredictable type 1 magic trick. It was a highly predictable mathematical second-order effect of a feedback loop that simply operated outside the engineer's assumed boundary of responsibility. SE8 demands that engineers map those loops and register those consequences before launch.
But what about the consequences that aren't a surprise? What about the damage a system does that the engineers know is going to happen?
That is SEP9.
Right. Ethical consequence analysis. This principle requires engineers to explicitly evaluate the ethical implications of a system's foreseeable effects, including the fully intended ones. The verifiable output is an ethical consequence register, where acceptance decisions are formally recorded by named individuals.
I think it is crucial to note that SEP9 explicitly separates this register from standard risk management. Ethical consequences are not a subset of technical risk.
How so?
If you reduce an ethical harm to a color-coded risk score on a spreadsheet, you strip it of its moral weight and you hide the human beings making the decision.
Can you give an example of how that plays out?
Take a facial recognition system deployed by law enforcement in a public space. We know, mathematically based on the training data, that the system will misidentify innocent people at a specific quantifiable rate.
Right, false positives.
Exactly. Those false positives are not an accident. They're an intended design trade-off made to achieve a certain level of operational speed. The burden of that trade-off falls squarely on citizens who never consented to be part of the system's environment. SEP9 asserts that accepting that harm requires a moral judgment and explicit personal accountability from the designers, not just a technical mitigation plan.
But here is where the manuscript shows a lot of intellectual honesty. Kasser points out a known gap regarding this ethical principle, doesn't he?
He does. Kasser correctly notes that the foundational layer A, the system's axioms, are purely descriptive. They describe the physics and logic of how systems operate. But they don't contain a normative moral claim. Gravity doesn't care if a system is ethical.
Science tells us what is, not what we ought to do.
Exactly. So, to properly ground SEP9 in actual science, Kasser proposes that future iterations of this framework need to adopt a new axiom.
Axiom 11.
Yes. A proposed axiom 11, which would formally state that designers bear inherent responsibility for the foreseeable consequences of their artificial systems. Until the community agrees to adopt that axiom, SEP9 stands as a vitally necessary ethical principle that is still waiting for its formal scientific anchor.
It's a fascinating structural problem. So taking a step back, what does this massive paradigm shift mean for you listening right now? Whether you are managing an engineering team, developing complex software architectures, or just trying to navigate the incredibly complicated, interconnected systems of our modern world, this framework offers a profound shift in perspective.
It really does.
The ultimate takeaway is that the individual, isolated parts of a system matter far less than the interactions between those parts. If you focus solely on optimizing the components, you will always inevitably be surprised by the behavior of the whole.
It's a rigorous lens for looking at the world. And as we conclude, we must reiterate our starting point. The 4-layer framework and these 9 principles are a proposed foundation.
Right.
Joseph Kasser published this draft manuscript to spark a fire. It is meant to invite challenge, rigorous debate, and collaborative refinement from the global engineering community to finally give the discipline the scientific bedrock it has lacked for 70 years.
It's an open invitation to build a better discipline, which leaves us with a final provocative thought for you to mull over. We've spent this deep dive talking about the absolute necessity of mapping predictable consequences, enforcing boundaries, and explicitly owning ethical trade-offs before a system ever sees the light of day.
Yeah.
If the global tech world were to formally adopt this framework, making unintended consequence registers and explicit ethical accountability a mandatory, verifiable output of every engineering project, how would that completely upend the speed, the culture, and the deeply entrenched financial models of the modern move fast and break things industry? Is true system science even compatible with our current economic incentives? We will leave you to think about that. Thanks for joining us on this deep dive.
I hope you enjoyed today's deep dive. Why not take a moment and join the discussion in the LinkedIn group Tackling Complex Problems. Take care.